In this lesson, you will learn about Auto Discovery VPN, Advpn. In this lesson, you will learn how to do the following. Configure and test Auto Discovery VPN with IBGP, and use the IKE Real-Time Debug to troubleshoot Advpn problems. Why should you use Advpn? To find the answer, we will review the most common VPN topologies. One point-to-multipoint topology variation is called hub and spoke. As its name describes, all clients connect through a central hub, similar to the way spokes connect to hubs on wheels. In the example shown on this slide, each client, or spoke, is a branch office FortiGate. For each branch office to reach another branch office, its traffic must pass through the hub. One advantage of using this topology is that it can easily manage the VPN configuration and firewall policies. Also, system requirements are minimal for the FortiGate devices that function as branch offices, because each FortiGate must maintain only one tunnel, or 2 SAs. In this example, 4 tunnels, or 8 SAs, are necessary in the hub. A disadvantage of using this topology is that communication between branch offices through headquarters is slower than it would be using a direct connection, especially if HQ is physically distant, as it can be for global companies. For example, if your company's HQ is in Brazil, and your company also has offices in Japan and Germany, latency can be significant. Another disadvantage is lack of redundancy. For example, if the FortiGate at HQ fails, the VPN fails company-wide. Also, FortiGate at HQ must be more powerful, as it handles 4 tunnels simultaneously, or 8 SAs. This slide shows a VPN that has a mesh topology. There are 2 types of mesh topology. Full mesh connects every location to every other location. Like the previous hub and spoke example, the example on this slide shows only 5 locations. In order to fully interact, each FortiGate needs 4 VPN tunnels, or 8 SAs, to the other FortiGate devices. This equals 3 more tunnels for each spoke FortiGate. In total, 20 tunnels are needed. If your company were to expand to 6 locations, it would require 30 VPNs. 7 locations would need 42 VPNs, and so on. This topology causes less latency and requires much less HQ bandwidth than hub and spoke. What are its disadvantages? Every spoke FortiGate must be more powerful. Additionally, both administration and troubleshooting get more complicated. Partial mesh attempts to compromise, minimizing required resources as well as latency. Partial mesh can be appropriate if communication is not required between every location. However, each FortiGate's configuration is still more complex than hub and spoke. Routing, especially, may require extensive planning. So, in general, if your company has many locations, hub and spoke will be cheaper, but slower, than a mesh topology. Mesh topologies place less strain on the central location and can be more fault-tolerant, but are also more expensive. Auto Discovery VPN was introduced in FortiOS 5.4. It combines the benefits of hub and spoke and full mesh topologies, because all the spoke-to-spoke tunnels are dynamically created on demand. Advpn supports single or multiple hub architectures. NAT is supported for the on-demand tunnels, as long as one of the spokes is not behind NAT. Advpn requires the use of a routing protocol. Currently it supports internal BGP and RIP version 2, RIP-NP. Both IP version 4 and IP version 6 are supported. This slide shows an example of how Advpn works. An administrator configures IPsec VPNs in multiple FortiGate devices to form VPN hub and spoke topologies. In this example, there are two hubs. Hub 1 has 3 spokes. Hub 2 has 2 spokes. There is also a VPN connecting both hubs. The dynamic tunnels between spokes are created on demand. Let's say that a user in Boston sends traffic to London. Initially, the direct tunnel between Boston and London has not been negotiated. So, the first packets from Boston to London are routed through Hub 1 and Hub 2. When Hub 1 receives those packets, it notices that Advpn is enabled in all the VPNs all the way to London. So Hub 1 sends an IKE message to Boston, informing that it can try to negotiate a direct connection to London. On receipt of this IKE message, Boston creates a FortiOS-specific IKE information message that contains its public IP address, its local subnet, the desired destination subnet, in other words, London's subnet, and an auto-generated PSK. Alternatively, digital certificate authentication can also be used. This IKE message is sent to London through Hub 1 and Hub 2. When London receives the IKE message from Boston, it stores the PSK and replies with another IKE information message that contains London's public IP address. After the reply arrives in Boston, the dynamic tunnel is negotiated between both peers. The negotiation succeeds because London is expecting a connection attempt from Boston's public IP address. Let's look at the IKE messages that are exchanged when an on-demand tunnel is being negotiated. The client behind Spoke 1 generates traffic for devices located on Spoke 2's network. Spoke 1 receives the packet, encrypts it, and sends it to the hub. The hub receives the packet from Spoke 1 and forwards it to Spoke 2. Spoke 2 receives the packet, decrypts it, and forwards it to the destination device. The hub notices that a more direct tunnel option might be available from Spoke 1 to Spoke 2. The hub sends a shortcut offer message to Spoke 1. Spoke 1 acknowledges the shortcut offer by sending a shortcut query to the hub. The hub forwards the shortcut query message to Spoke 2. Spoke 2 acknowledges the shortcut query and sends a shortcut reply to the hub. The hub forwards the shortcut reply to Spoke 1, and Spoke 1 and Spoke 2 initiate the tunnel IKE negotiation. As mentioned, Advpn requires the use of a routing protocol. In the next slides, you will learn how to configure Advpn with internal BGP. As an example, you will use an internal BGP topology made up of one hub with 2 spokes. All the devices are in the AS65100. This slide shows the following Advpn configuration in the hub. Disable set add route to ensure that the hub will not automatically install routes to the spokes after their tunnels open. Enable Advpn with the command auto discovery sender. Assign an IP address to the IPsec virtual interface. This is a requirement for having a dynamic routing protocol over IPsec. For the remote IP, use any dummy IP address not being used by any spoke. For the Phase 2 configuration, ensure that quick modes are set to all 0.0.0.0/0.0.0.0. Set a firewall policy to allow the traffic from the spokes to the hub, from the hub to the spokes, and between spokes through the hub. This slide shows the following Advpn configuration in the hub. Enable Advpn with the command auto discovery receiver. Assign an IP address to the IPsec virtual interface. Add a static route to a summarized subnet that contains all the IPsec virtual IP addresses. This slide shows the following internal BGP configuration in the hub. Configure a BGP neighbor group. All the spokes are a part of it. Create a neighbor range with a prefix that includes all the spokes. In this way, you do not need to define each spoke individually as a neighbor. If you are using internal BGP for Advpn, you must configure the hub as a route reflector. So routes learned from one spoke are forwarded to the other spokes. Add the local networks behind the hub to be advertised over BGP. This slide shows the following internal BGP configuration in one of the spokes. Configure the hub as a BGP neighbor. Define the internal network that will be advertised over the BGP. If you are configuring Advpn on FortiManager using the VPN Manager, remember the following. Set the protected networks to all. Use scripts to enable Advpn in Phase 1. Disable the option Add Route on the hub. Configure IP addresses on the IPsec virtual interfaces. Add a summarized static route on all spokes for the IPsec virtual interfaces, and configure dynamic routing. If you are using internal BGP, use a script to enable route reflector on the hub. The configuration of the protected subnet is under VPN communities. For Advpn, disable Add Route under the VPN gateway configuration of the hub. This prevents the hub from adding routes based on IKE negotiations. For that purpose, Advpn uses a dynamic routing protocol instead. After the tunnels between the hub and the spokes are open, you can run the following commands in the spokes to verify that routing updates are taking place. Get router info BGP network. Get router info routing table all. This slide shows that spoke 1 learned the routes to the hubs and to the networks of spoke 2 through BGP. Spoke 2 is currently accessible through the hub. If you run the IKE real-time debug during the negotiation of an Advpn tunnel, you see the exchange of all shortcuts. This slide shows an example of the output of the real-time debug in the hub. You can see the shortcut offer being sent, and the shortcut's query and reply being received and forwarded. This slide shows the IKE real-time debug output from one spoke when the on-demand tunnel is triggered. The first two messages indicate that a shortcut offer is received from the hub. After that, a shortcut query message is sent. A shortcut reply message is received, and the dynamic tunnel interface is created. Using the command get ipsec tunnel list, you can verify which on-demand tunnels are open. It is important to note that on-demand tunnels remain active until their SAs are manually flushed, or until they time out. This slide shows the routing table after the on-demand tunnel is open. We can confirm that the network of spoke 2 is directly accessible using the on-demand tunnel VPN 00. In this lesson, you learned how to do the following: configure Advpn and troubleshoot Advpn.